This is an outline of a solution for problem 11.2.7. This is similar to exercise 7 in homework 5. In this problem, we're given two sets of measurements. We're firing some kind of shell from a gun, cannon. For each shell, two measurements are recorded using two different devices. So there's some kind of measurement device A, there's some kind of measurement device B. Let me draw a picture to illustrate what I think is going on here. Two different measuring devices measuring velocity. Here's a picture. You will now see my lack of artistic talent. So we have some kind of a gun. Here's a gun. And it's on some kind of platform. So we have a gun on the platform, and it's shooting out these shells. So we have these shells that's shooting out. Okay, so far, we have two devices. We have a device A, which is looking at the shell. See how would I draw that? An eye looking at the shell and measuring the velocity. Then we have a second device, device B. And device B is also looking at this shell. And device B is also measuring the velocity. So if we go back to the problem, device A said 790.6. So for shell number 1, device A says it's going at 790.6, and device B says nope, it's going at 788.7. So device B says nope, it's going at 788.7. So this is the setup. We have one single bullet going out, and we have two measurements taken of that one bullet. So this is paired. We have a data set A that consists of a bunch of measurements. We have a data set B, which consists of a bunch of measurements, and they're related. The first number are the two measurements for shell number 1. The second two are the two measurements for shell number 2. So this is matched pairs, or dependent. Let's go back to the problem. Why are these matched pairs data? Well, because observation 1 is on the same bullet, observations 2 are on the same bullet, so the same round was fired at every trial. I don't think that's what it means. This is like saying that we've collected the bullet and refired it. The two measurements are taken on the same round. Yes, A and B are taken on the same bullet going out. All the measurements came from rounds fired from the same gun That's true, but that's irrelevant. They're all from the same gun. Measurements are taken by the same instrument. Choice D, that's false. The whole purpose of this is that there are two different instruments, A and B, and we're comparing them. So these are matched pairs because we have two different measurements on the same thing. They're paired. Let's keep going. Is there a difference in the measurements at O1? The note normal works. Differences are approximately normal, no outliers. So what the note says is, yes, we can use our usual techniques. Now let's compute the numbers that we need to solve the rest of the problems using Excel. If you're very observant, you'll see that the numbers in our database here are different. That's because I used those numbers for the StatCrunch solution. Then I hit similar problem, and I'm going to use these numbers for the Excel solution. So the next part, is there a difference, a significant difference at the alpha equals O1 level? What we need to do is to look at this as paired data, do a difference, and then do the hypothesis test on the pair. Is there a difference means, is the difference in means 0? So let's click this to copy the table and open it in Excel. And here it is in Excel. This is very convenient in that we don't have to type the numbers in ourselves. So remember, how do we analyze matched pairs or dependent? What we do is subtract to get the difference per observation. That gives us a single number, and do a hypothesis test on the mean. The null hypothesis being the difference is equal to 0. So let's do the differences. A minus B, not hard, equals A, I'm clicking that, minus B, I'm clicking that. And we can check 794.6 minus 793.1 is indeed 1.5. Now I'm going to take this formula, do a Control-C copy, and paste for the other 5 observations, a Control-V for paste. So here are the differences. I want to test whether the mean is 0 or not. So to do that, the test statistic is the mean over the standard error, where the standard error is the standard deviation over the square root of n. So what do we need to calculate? First of all, we need to calculate the mean. So let's put that here. In Excel, that's average of all these values. The average is minus 0.31, blah, blah, blah. Next, to calculate the standard error, I need the standard deviation. That's STDEV. In Excel, I'll highlight everything. 5.30 something. then the square root of n, n is 6, there are 6 observations, equals square root of n. Sorry, square root of 6. So now I need to calculate the mean over the standard error. It's actually the mean minus the target, but the target is 0. So the test statistic is equal to the mean difference divided by parentheses standard deviation over square root of n. See, this one, h3 over h4, is the standard deviation over the square root of n. That's the standard error. So the test statistic is minus 0.14, etc. Automatically, we know that this is going to be a do not reject. A test statistic of 1 is a typical distance away from the mean. Here we're even closer than the typical distance, so it's got to be a do not reject. In any case, let's do the critical value and let's do the p calculation. Is there a difference in measurement? In other words, is the null hypothesis equal to 0? The alternative hypothesis is different from 0. So this is a two-tailed test. So the critical value is T inverse, the probability of, alpha equals 0.01, you see? .01 with 5 degrees of freedom, one less than the number of data values. So 4 point whatever. This is using the old version of the function T inverse. The new version is equal to T dot inverse dot 2T for two tails, probability 0.1 and 5 degrees of freedom again. And we get the same number, of course. Since the actual distance we're away, minus 0.1 something, is less than the distance we're allowed to be away, which is 4 point something, this is going to be a do not reject. Using the classical method. How about the p-value method? The p-value method measures how far away we are and the probability of being that far or further, equals t dist the x, I'll click on the x, the degrees of freedom 5, and two-tailed 2. Doesn't work. That's because the old version only takes positive values for the test statistic. So let's try again. Equals t dist of the positive value of that, which is minus the negative value, degrees of freedom 5, and tails 2. So this is the p-value. To reject, we only reject when the p-value is less than 0.1. So again, this is a do not reject. And the p-value method. This is the old version of t-dist, the one that works for all Excel versions. The new one we could use equals t dot dist dot two tails, 2t, the x comma degrees of freedom, 5. Whoops, it's not true. It does not accept negative values. So I have to put in a negative for the test value. We get the same number. So in terms, if we use the p-value method, we also get a do not reject. Let's go back to MyStatLab. Is there a difference? No, there is no significant difference using either the classical method or the p-value method. We check. That's correct. Now let's go on to the next part. Done. Continue. Construct a 99% confidence interval. Compute the difference for a minus b. Round to 3 decimals. So a 99% confidence interval is, I'll take this further up, 99% confidence interval is the x bar minus the critical value times the standard error to x bar plus the critical value times the standard error. In other words, we start off with x bar, which is the actual measured mean, and we go down by this many steps, critical value, and we start with x bar and we go up that many steps, where each step is a standard error. Equals x bar the mean minus the critical value times the standard error, which is standard deviation over square root of n. It's hard to see, so let me go up a little bit more. This is H2, which is the mean, minus H8, which is the critical value, times H3 over H4, standard deviation over the square root of n, which is the standard error. The upper limit is exactly the same, except it's plus. So it's equal to the sample mean plus the critical value times the standard error, which is s over the square root of n. So here is a 99% confidence interval. I think the problem wanted that to 3 decimals. So we have minus 9.042 to positive 8.408. So 9042 minus 9.042 to positive 8.408. 8.408. We check our answer. Well done. Let's now go to the last part. Choose the statement that best agrees with your interpretation. Now remember, we did a 99% confidence interval. That's the one that corresponds with alpha equals 0.1. Hypothesis tests talk about the part that doesn't work, the 1%, listed as a decimal. Confidence intervals talk about the part that does work, as a percentage. It has to be 99% confident. Not sure what the 17% came from, but it's 99% confident that the mean difference is there. These are all the reasonable numbers. I'm 99% confident of that. Check our answer. Good job. That's the end of the question.